here, I can solve for alpha and beta, and then I can plug in 0, 1, 2, 3, 4, 5, even 1,000, and get the value of this function. Okay, so let's take a look at that. So you can see what we did here. So we have a1 is equal to 7, so we say 7 is equal to 2 alpha plus 3 beta, as we just talked about. And using a0 is equal to 1, we get 1 is equal to alpha plus beta. So I can do a few things. One of the simplest things to do in this case, I can simply make a substitution. Since alpha plus beta is 1, then alpha is equal to 1 minus beta. Since alpha is equal to 1 minus beta, I can substitute alpha with 1 minus beta right here. So it's 2 times 1 minus beta, plus 3 beta is equal to 7, beta is equal to 5. Once I know that, since I know that alpha plus beta is equal to 1, then I know that alpha must be equal to negative 4, because combined they must equal 1. So therefore, now what we do is we go back to our general solution and we substitute alpha and beta with the actual values based upon the initial conditions. So therefore, I'm going to get 5, which is the value for beta. I put that first. 5 times 3 to the n minus 4, which is our alpha, times 2 to the n. I flipped them around. I could write minus 4, 2 to the n, plus 5 times 3 to the n. That's a little more awkward. This looks a little bit more normal. So let's find out if this is going to work. Do you remember what the value of a0 was? a0 was?
1.
It's 1. So that means a0 should be equal to 3 to the 0, 2 to the 0 is 1, so it's 5 minus 4. Correct. Okay. What about a1? 7. So 3 to the 1 is 3, 2 to the 1 is 2. So 15 minus 8 is 7. So let's compute, for example, another one. Like, for example, so we know a0, a1 works. This is a very good thing, because that means it's matching the initial conditions. So notice here, if I want to do a2, a2 will be 5 times a1 minus 6 times a2, which is going to be 5 times 7, which is 35, minus 6 is 29, and if I just plug it directly to the formula, I'll get 5 times 9, right, which is 5 times 9 is 45, minus 16, which gives me 29. So this is directly computed, this is recurrently computed. So if you didn't solve this recurrence, and I said, what is a sub 10, you'd be working on this all day. But if you solve this problem, you can simply say it's going to be 3 to the 10th power times 5 minus 4 times 2 to the 10th power. You're done. That's the value. So getting a closed form for our recurrence complexity. Let's look at another example. So another very famous sequence is called the Fibonacci sequence. So Fibonacci sequence is very, very interesting. It basically says, by the way, there's I don't know why it didn't come out, but this should be a of n is equal to a n minus 1 plus. It's going to be a plus. For some reason, it looks like a minus, but it's actually a plus. But it doesn't print out that way. You see it. Okay, so it's the nth term is equal to the sum of the previous two terms. The 8th term is the 7th plus the 6th. The 9th is 8th plus the 7th, etc. So therefore, our initial conditions for Fibonacci sequence is actually a0 is 0, and a1 is 1. Those are the true initial conditions for Fibonacci. So we will solve it exactly the same way as we just solved it. We'll let a to the n, an equal to r to the n. We will always solve this the same way. If we can't solve this way, we're not going to solve it. Okay? But you will see all the problems I'm going to give you are going to be solvable. So doing that, we basically get r to the n, substitution, r to the n minus 1 plus r to the n minus 2, remember it's the plus.